Metamaterials are smart materials engineered to have properties that have not yet been found in nature. They are made from assemblies of multiple elements fashioned from composite materials such as metals or plastics. The materials are usually arranged in repeating patterns, at scales that are smaller than the wavelengths of the phenomena they influence. Metamaterials derive their properties not from the properties of the base materials, but from their newly designed structures. Their precise shape, geometry, size, orientation and arrangement gives them their smart properties capable to manipulate electromagnetic waves by blocking, absorbing, enhancing, bending waves, to achieve benefits that go beyond what is possible with conventional materials. Appropriately designed metamaterials can affect waves of electromagnetic radiation or sound in a manner not observed in bulk materials. Those that exhibit a negative index of refraction for particular wavelengths have attracted significant research. These materials are known as negative index metamaterials. Potential applications of metamaterials are diverse and include optical filters, medical devices, remote aerospace applications, sensor detection and infrastructure monitoring, smart solar power management, crowd control, radomes, high-frequency battlefield communication and lenses for high-gain antennas, improving ultrasonic sensors, and even shielding structures from earthquakes. Metamaterials offer the potential to create superlenses. Such a lens could allow imaging below the diffraction limit, that is the minimum resolution that can be achieved by a given wavelength. A form of invisibility was demonstrated using gradient index materials. Acoustic and seismic metamaterials are also research areas. Metamaterial research is interdisciplinary and involves such fields as electrical engineering, electromagnetics, classical optics, solid-state physics, microwave and antenna engineering, optoelectronics, material sciences, nanoscience and semiconductor engineering. History. Explorations of artificial materials for manipulating electromagnetic waves began at the end of the 19th century. Some of the earliest structures that may be considered metamaterials were studied by Jagadish Chandra Bose, who in 1898 researched substances with chiral properties. Carl Ferdinand Lindemann studied wave interaction with metallic helices as artificial chiral media in the early 20th century. Winston E. Koch developed materials that had similar characteristics to metamaterials in the late 1940s. In the 1950s and 1960s, artificial dielectrics were studied for lightweight microwave antennas. Microwave radar absorbers were researched in the 1980s and 1990s as applications for artificial chiral media. Negative index materials were first described theoretically by Victor V. Zeligo in 1967. He proved that such materials could transmit light. He showed that the phase velocity could be made anti-parallel to the direction of pointing vector. This is contrary to wave propagation in naturally occurring materials. John Pendry was the first to identify a practical way to make a left-handed metamaterial, a material in which the right-hand rule is not followed. Such a material allows an electromagnetic wave to convey energy against its phase velocity. Pendry's idea was that metallic wires aligned along the direction of a wave could provide negative permittivity. Natural materials display negative permittivity. The challenge was achieving negative permeability. In 1999, Pendry demonstrated that a split ring with its axis placed along the direction of wave propagation could do so. In the same paper, he showed that a periodic array of wires and rings could give rise to a negative refractive index. Pendry also proposed a related negative permeability design, the Swiss roll. In 2000, Smith et al. Reported the experimental demonstration of functioning electromagnetic metamaterials by horizontally stacking, periodically, split ring resonators and thin wire structures. A method was provided in 2002 to realize negative index metamaterials using artificial lumped element loaded transmission lines in microstrip technology. In 2003, complex negative refractive index and imaging by flat lens using left-handed metamaterials were demonstrated. By 2007, experiments that involved negative refractive index had been conducted by many groups. At microwave frequencies, the first, imperfect invisibility cloak was realized in 2006. Electromagnetic metamaterials. An electromagnetic metamaterial affects electromagnetic waves incident on it via structural features that are smaller than the wavelength. To behave as a homogeneous material accurately described by an effective refractive index, its features must be much smaller than the wavelength. For microwave radiation, the features are on the order of millimeters. Microwave frequency metamaterials are usually constructed as arrays of electrically conductive elements that have suitable inductive and capacitive characteristics. One microwave metamaterial is a suitably scaled split-ring resonator. Photonic metamaterials, nanometer scale, manipulate light at optical frequencies. To date, subwavelength structures have shown only a few, questionable, results at visible wavelengths. Photonic crystals and frequency-selective surfaces such as diffraction gratings, dielectric mirrors and optical coatings exhibit similarities to subwavelength structured metamaterials. However, these are usually considered distinct from subwavelength structures, as their features are structured for the wavelength at which they function and thus cannot be approximated as a homogeneous material. However, material structures such as photonic crystals are effective in the visible light spectrum. The middle of the visible spectrum has a wavelength of approximately 560 nanometers. Photonic crystal structures are generally half this size or smaller, that is less than 280 nanometers. Plasmonic metamaterials utilize surface plasmons, which are packets of electrical charge that collectively oscillate at the surfaces of metals at optical frequencies. Frequency-selective surfaces can exhibit subwavelength characteristics and are known variously as artificial magnetic conductors or high-impedance surfaces. FSS display inductive and capacitive characteristics that are directly related to their subwavelength structure. Negative refractive index. Almost all materials encountered in optics, such as glass or water, have positive values for both permittivity epsilon and permeability micro. However, metals such as silver and gold have negative permittivity at shorter wavelengths. A material such as a surface plasmon that has either epsilon or micro negative is often opaque to electromagnetic radiation. However, anisotropic materials with only negative permittivity can produce negative refraction due to chirality. Although the optical properties of a transparent material are fully specified by the parameters epsilon r and micro r, refractive index n is often used in practice, which can be determined from all known non-metamaterial transparent materials possess positive epsilon r and micro r. By convention, the positive square root is used for n. However, some engineered metamaterials have epsilon r less than 0 and micro r less than 0. Because the product epsilon r micro r is positive, n is real. Under such circumstances, it is necessary to take the negative square root for n. The foregoing considerations are simplistic for actual materials, which must have complex-valued epsilon r and micro r. The real parts of both epsilon r and micro r do not have to be negative for a passive material to display negative refraction. Metamaterials with negative n have numerous interesting properties. Snell's law, that as n2 is negative, the rays are refracted on the same side of the normal on entering the material. Cherenkov radiation points the other way. The time-averaged pointing vector is anti-parallel to phase velocity. However, for waves to propagate, a micro must be paired with her epsilon in order to satisfy the wave number dependence on the material parameters. Negative index of refraction derives mathematically from the vector triplet E, H and K. For plane waves propagating in electromagnetic metamaterials, the electric field, magnetic field and wave vector follow a left-hand rule, the reverse of the behavior of conventional optical materials. Classification: electromagnetic metamaterials are divided into different classes, as follows. Negative index: in negative index metamaterials, both permittivity and permeability are negative, resulting in a negative index of refraction. These are also known as double negative metamaterials or double negative materials. Other terms for NIMs include left-handed media, media with a negative refractive index, and backward wave media. In optical materials, if both permittivity epsilon and permeability micro are positive, wave propagation travels in the forward direction. If both epsilon and micro are negative, a backward wave is produced. If epsilon and micro have different polarities, waves do not propagate. Mathematically, quadrant 2 and quadrant IV have coordinates in a coordinate plane where epsilon is the horizontal axis, and micro is the vertical axis. To date, only metamaterials exhibit a negative index of refraction. Single negative metamaterials have either negative relative permittivity or negative relative permeability, but not both. They act as metamaterials when combined with a different, complementary SNG, jointly acting as a DNG. Epsilon negative media display a negative epsilon R while micro R is positive. Many plasmas exhibit this characteristic. For example, noble metals such as gold or silver are Eng in the infrared and visible spectrums. Mu negative media display a positive epsilon R and negative micro R. Gyrotropic or gyromagnetic materials exhibit this characteristic. A gyrotropic material is one that has been altered by the presence of a quasi-static magnetic field, enabling a magneto-optic effect. A magneto-optic effect is a phenomenon in which an electromagnetic wave propagates through such a medium. In such a material, left and right rotating elliptical polarizations can propagate at different speeds. When light is transmitted through a layer of magneto-optic material, the result is called the Faraday effect. The polarization plane can be rotated, forming a Faraday rotator. The results of such a reflection are known as the magneto-optic Kerr effect. Two gyrotropic materials with reversed rotation directions of the two principal polarizations are called optical isomers. Joining a slab of Eng material and slab of MNG material resulted in properties such as resonances, anomalous tunneling, transparency and zero reflection. Like negative index materials, SNGs are innately dispersive, so their epsilon R, micro R and refraction index N are a function of frequency. Bandgap electromagnetic bandgap metamaterials control light propagation. This is accomplished either with photonic crystals or left-handed materials. PCs can prohibit light propagation altogether. Both classes can allow light to propagate in specific, designed directions, and both can be designed with band gaps at desired frequencies. The period size of EBGs is an appreciable fraction of the wavelength, creating constructive and destructive interference. PC are distinguished from sub-wavelength structures, such as tunable metamaterials, because the PC derives its properties from its bandgap characteristics. PCs are sized to match the wavelength of light, versus other metamaterials that expose sub-wavelength structure. Furthermore, PCs function by diffracting light. In contrast, metamaterial does not use diffraction. PCs have periodic inclusions that inhibit wave propagation due to the inclusion's destructive interference from scattering. The photonic bandgap property of PCs makes them the electromagnetic analog of electronic semiconductor crystals. EBGs have the goal of creating high-quality, low-loss, periodic, dielectric structures. An EBG affects photons in the same way semiconductor materials affect electrons. PCs are the perfect bandgap material, because they allow no light propagation. Each unit of the prescribed periodic structure acts like one atom, albeit of a much larger size. EBGs are designed to prevent the propagation of an allocated bandwidth of frequencies, for certain arrival angles and polarizations. Various geometries and structures have been proposed to fabricate EBGs' special properties. In practice, it is impossible to build a flawless EBG device. EBGs have been manufactured for frequencies ranging from a few gigahertz to a few terahertz, radio, microwave and mid-infrared frequency regions. EBG application developments include a transmission line, wood piles made of square dielectric bars and several different types of low-gain antennas. Double positive mediums do occur in nature, such as naturally occurring dielectrics. Permittivity and magnetic permeability are both positive and wave propagation is in the forward direction. Artificial materials have been fabricated which combine DPS, Eng and MNG properties. Bi-isotropic and bi-anisotropic categorizing metamaterials into double or single negative, or double positive, normally assumes that the metamaterial has independent electric and magnetic responses described by epsilon and micro. However, in many cases, the electric field causes magnetic polarization, while the magnetic field induces electrical polarization, known as magneto-electric coupling. Such media are denoted as bi-isotropic. Media that exhibit magneto-electric coupling and that are anisotropic are referred to as bi-anisotropic. Four material parameters are intrinsic to magneto-electric coupling of bi-isotropic media. They are the electric and magnetic field strengths, and electric and magnetic flux densities. These parameters are epsilon, micro, kappa and chi, or permittivity, permeability, strength of chirality, and the Telegen parameter respectively. In this type of media, material parameters do not vary with changes along a rotated coordinate system of measurements. In this sense they are invariant or scalar. The intrinsic magneto-electric parameters, kappa and chi, affect the phase of the wave. The effect of the chirality parameter is to split the refractive index. In isotropic media this results in wave propagation only if epsilon and micro have the same sign. In bi-isotropic media with chi assumed to be 0, and kappa a non-zero value, different results appear. Either a backward wave or a forward wave can occur. Alternatively, two forward waves or two backward waves can occur, depending on the strength of the chirality parameter. In the general case, the constitutive relations for bi-anisotropic materials read wherein are the permittivity and the permeability tenses, respectively, whereas in are the two magneto-electric tenses. If the medium is reciprocal, permittivity and permeability are symmetric tenses, and whereas the chiral tensor describing chiral electromagnetic and reciprocal magneto-electric response. The chiral tensor can be expressed as, whereas the trace of I is the identity matrix, N is a symmetric trace-free tensor, and J is an antisymmetric tensor. Such decomposition allows us to classify the reciprocal bi-anisotropic response, and we can identify the following three main classes: chiral media, pseudo-chiral media, omega media. Rizza al. Suggested 1D chiral metamaterials where the effective chiral tensor is not vanishing if the system is geometrically one-dimensional. Chiral metamaterials are constructed from chiral materials in which the effective parameter K is non-zero. This is a potential source of confusion as the metamaterial literature includes two conflicting uses of the terms left and right-handed. The first refers to one of the two circularly polarized waves that are the propagating modes in chiral media. The second relates to the triplet of electric field, magnetic field and pointing vector that arise in negative refractive index media. which in most cases are not chiral. Wave propagation properties in chiral metamaterials demonstrate that negative refraction can be realized in metamaterials with a strong chirality in positive epsilon and mu. This is because the refractive index has distinct values for left and right. Given by it can be seen that a negative index will occur for one polarization if kappa greater than square root epsilon r micro r. In this case, it is not necessary that either or both epsilon r and micro r be negative for backward wave propagation. FSS-based frequency selective surface-based metamaterials block signals in one waveband and pass those at another waveband. They have become an alternative to fixed-frequency metamaterials. They allow for optional changes of frequencies in a single medium, rather than the restrictive limitations of a fixed-frequency response.